an AI-generated post for your viewing pleasure. Tired of your large language models choking on lengthy input sequences? The solution may lie in training them over text that's been compressed to the extreme, without compromising their ability to learn. New research shows it's possible, but subword tokenizers still have the edge. The seemingly insatiable appetite of today's large language models for textual data has led researchers to seek ever more efficient ways to feed these models the information they crave. While standard subword tokenizers can compress text by a factor of 4 or so, a team of researchers has now demonstrated that by using neural text compressors, they can achieve compression rates of up to 12x, all while keeping the resulting tokens learnable by downstream large language models. It's an enticing prospect. By packing more raw text into each token, large language models could model longer-range dependencies, ingest more pre-training data, and generate more text per inference step, all without increasing the computational burden. But as the researchers discovered, the path to realizing these benefits is fraught with challenges. Their work sheds new light on the delicate balance required to make highly compressed text learnable by powerful language models. At the heart of the researchers' approach is the idea of using a small M1 language model to compress the text, and then training a larger M2 model to learn from that compressed representation. The M1 model serves as the compression engine, using a technique called arithmetic coding to transform the text into a dense bitstream. The trouble is, that bitstream often ends up looking like little more than random noise, a problem the researchers dubbed the learnability challenge. As it turns out, the more effectively M1 compresses the text, the harder it becomes for M2 to extract meaningful patterns from the output. The researchers find that standard large language models simply can't learn to model text that's been compressed using arithmetic coding in a straightforward way. To address this, the researchers propose a clever modification called equal info windows. Instead of compressing the entire text sequence at once, they break it into smaller chunks, each of which is compressed independently. Crucially, they ensure that each chunk contains roughly the same amount of information, making the overall bitstream more amenable to learning. This simple tweak pays dividends. The researchers' best equal info windows model not only outperforms standard byte-level baselines on perplexity benchmarks, but it does so while using significantly fewer computational operations per byte of input, a key metric for serving efficiency. However, the model still falls short of the performance achieved by subword tokenizers like SentencePiece, which the researchers attribute to the relative instability of the mappings between words and tokens in their neural compression approach. While previous work has explored using large language models for compression, the current study is the first to tackle the challenge of training subsequent models directly over the compressed output. This represents a crucial step towards realizing the full benefits of neural text compression, which include not just storage and transmission efficiency, but also the potential for large language models to model longer-range dependencies and generate more text per inference step. The researchers' detailed analysis of the factors affecting learnability, from the inherent difficulty of learning the arithmetic coding algorithm to the importance of stable token-to-text mappings, provides valuable insights that can guide future research in this area. They're finding that increasing the vocabulary size of the neural tokenizers generally improves performance, except in the case of GSIP compressed data, points to the crucial role played by the coding component of the compression algorithm. Compared to prior work on token-free language modeling, which is focused on techniques like convolutional downsampling, the researchers' approach of learning discrete tokenization end-to-end represents a distinct and promising direction. By aiming to encode an equal amount of information per token, they introduce a new bias that could lead to more effective compression schemes tailored for large language model training. As the researchers note, their findings conflict with recent work showing byte-level models outperforming subword models at medium and large scales. This discrepancy highlights the importance of evaluating models in a way that aligns with the end goal. In this case, training large language models that achieve the best perplexity at whatever sequence length they can handle, given a fixed budget for training and inference. The researchers' work represents an important step forward in the quest to train large language models more efficiently by leveraging highly compressed text. While their equal info windows approach falls short of the performance achieved by standard subword tokenizers, it nevertheless demonstrates the potential of this line of research. By shedding light on the key factors that determine the learnability of compressed text, the researchers have laid the groundwork for future breakthroughs. As the field continues to push the boundaries of neural text compression, the ability to train powerful large language models over these highly efficient representations could unlock new levels of language understanding and generation, all while reducing the computational resources required. Whether the ultimate solution lies in further refinements of the equal info windows technique or in entirely new approaches to neural tokenization, one thing is clear. The race is on to find the perfect balance between compression and learnability. The researchers' work has brought us one step closer to that elusive goal, and the implications for the future of large language models are truly exciting.